Part 2 of the Mathematical Appendix. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This reading by Carl Manchester, 2008. Note 14. Let alpha 1, alpha 2, alpha 3, etc. be the several amounts of different kinds of labour, as for instance wood cutting, stone carrying, earth digging, etc., on the part of the man in question that would be used in building the house on any given plan, and beta, beta dash, beta double dash, etc., the several amounts of accommodation of different kinds, such as sitting rooms, bedrooms, offices, etc., which the house would afford on that plan. Then, using V and H as in the previous note, V, beta, beta dash, beta double dash are all functions of alpha 1, alpha 2, alpha 3, and so on, and H, being a function of beta, beta dash, beta double dash, is a function also of alpha 1, alpha 2, alpha 3. We have then to find the marginal investments of each kind of labour for each kind of use. The differential of V over the differential of A1 equals the differential of H over the differential of beta by the differential of beta over the differential of A1 equals the differential of H over the differential of beta dash by the differential of beta dash over the differential of A1 equals the differential of H over the differential of beta double dash by the differential of beta double dash over the differential of A1, and so on. These equations represent a balance of effort and benefit. The real cost to him of a little extra labour spent on cutting timber and working it up is just balanced by the benefit of the extra sitting room or bedroom accommodation that he could get by so doing. If, however, instead of doing the work himself, he pays carpenters to do it, we must take V to represent not his total effort, but his total outlay of general purchasing power. Then the rate of pay which he is willing to give to carpenters for further labour, his marginal demand price for their labour, is measured by the differential of V over the differential of A, while the differential of H over the differential of beta, the differential of H over the differential of beta dash, are the money measures to him of the marginal utilities of extra sitting room and bedroom accommodation respectively, that is, his marginal demand prices for them. And the differential of beta over the differential of A and the differential of beta dash over the differential of A are the marginal efficiencies of carpenters' labour in providing those accommodations. The equations then state that the demand price for carpenters' labour tends to be equal to the demand price for extra sitting room accommodation and also for extra bedroom accommodation, and so on, multiplied in each case by the marginal efficiency of the work of carpenters in providing that extra accommodation, proper units being chosen for each element. When this statement is generalized, so as to cover all the varied demand in a market for carpenters' labour, it becomes the marginal demand price for carpenters' labour is the marginal efficiency of carpenters' labour in increasing the supply of any product, multiplied by the marginal demand price for that product. Or to put the same thing in other words, the wages of a unit of carpenters' labour tends to be equal to the value of such part of any of the products to producing which their labour contributes, as represents the marginal efficiency of a unit of carpenters' labour with regard to that product, or, to use a phrase with which we shall be much occupied in Book 6, Chapter 1, it tends to be equal to the value of the net product of their labour. This proposition is very important and contains within itself the kernel of the demand side of the theory of distribution. Let us then suppose a master builder to have in mind to erect certain buildings, and to be considering what different accommodation he shall provide, as for instance dwelling houses, warehouses, factories, and retail shop room. There will be two classes of questions for him to decide: how much accommodation of each kind he shall provide, and by what means he shall provide it. Thus, besides deciding whether to erect villa residences offering a certain amount of accommodation, he has to decide what agents of production he will use, and in what proportions, whether, for example, he will use tile or slate, how much stone he will use, whether he will use steam power for making mortar, etc., or only for crane work, and if he is in a large town, whether he will have his scaffolding put up by men who make that work a speciality, or by ordinary labourers, and so on. Let him then decide to provide an amount beta of villa accommodation, an amount beta dash of warehouse, an amount beta double dash of factory accommodation, and so on, each of a certain class. But instead of supposing him to hire simply alpha 1, alpha 2, and so on, quantities of different kinds of labour, as before, let us class his expenditure under the three heads of 1. Wages, 2. Prices of raw material, and 3. Interest on capital, while the value of his own work and enterprise makes a fourth head. Thus let x1, x2, and so on be the amounts of different classes of labour, including that of superintendents, which he hires, the amount of each kind of labour being made up of its duration and its intensity. Let y1, y2, and so on be amounts of various kinds of raw materials which are used up and embodied in the buildings, which may be supposed to be sold freehold. In that case, the pieces of land on which they are severally built are merely particular forms of raw material from the present point of view, which is that of the individual undertaker. Next, let z be the amount of locking up, or appropriation of the employment, of capital for the several purposes. Here we must reckon in all forms of capital reduced to a common money measure, including advances for wages, for the purchase of raw material, also the uses, allowing for wear and tear, etc., of his plant of all kinds, his workshops themselves, and the ground on which they are built being reckoned on the same footing. The periods during which the various lockings up run will vary, but they must be reduced on a compound rate, i.e. according to geometrical progression, to a standard unit, say a year. Fourthly, let U represent the money equivalent of his own labour, worry, anxiety, wear and tear, etc., involved in the several undertakings. In addition, there are several elements which might have been entered under separate heads, but which we may suppose combined with those already mentioned. Thus the allowance to be made for risk may be shared between the last two heads. A proper share of the general expenses of working the business, supplementary costs, will be distributed among the four heads of wages, raw materials, interest on the capital value of the organisation of the business, its goodwill, etc., regarded as a going concern, and remuneration of the builder's own work, enterprise and anxiety. Under these circumstances, V represents his total outlay, and H his total receipts, and his efforts are directed to making H minus V a maximum. On this plan we have equations similar to those already given, viz. the differential of V over the differential of x1 equals the differential of H over the differential of beta multiplied by the differential of beta over the differential of x1 equals the differential of H over the differential of beta dash multiplied by the differential of beta dash over the differential of x1, and so on. That is to say, the marginal outlay which the builder is willing to make for an additional small supply delta x1 of the first class of labour, viz. the differential of V over the differential of x1 by delta x1, is equal to the differential of H over the differential of beta multiplied by the differential of beta over the differential of x1 by delta x1, i.e. to that increment of his total receipts H which he will obtain by the increase in the villa accommodation provided by him that will result from the extra small supply of the first class of labour. This will equal a similar sum with regard to warehouse accommodation, and so on. Thus he will have distributed his resources between various uses in such a way that he would gain nothing by diverting any part of any agent of production, labour, raw materials, the use of capital, nor his own labour and enterprise, from one class of building to another. Also, he would gain nothing by substituting one agent for another in any branch of his enterprise, nor indeed by any increase or diminution of his use of any agent. From this point of view, our equations have a drift very similar to the argument of Book 3, Chapter 5, as to the choice between the different uses of the same thing. Compare one of the most interesting notes F attached to Professor Edgeworth's brilliant address to the British Association in 1889. There is more to be said on the difficulty of interpreting the phrase net product of any agent of production, whether a particular kind of labour or any other agent, and perhaps the rest of this note, though akin to what has gone before, may be more conveniently read at a later stage. The builder paid the differential of V over the differential of x1 by delta x1 for the last element of the labour of the first group because that was its net product. If directed to building villas, it brought him the differential of h over the differential of beta multiplied by the differential of beta over the differential of x1 by delta x1 as special receipts. Now, if P be the price per unit which he receives for an amount beta of villa accommodation, and therefore P beta the price which he receives for the whole amount beta, and if we put for shortness the change in beta in place of the differential of beta over the differential of x1 by delta x1, the increase of villa accommodation due to the additional element of labour delta x1, then the net product we are seeking is not P by the change in beta, but P by the change in beta plus beta by the change in P, where the change in P is a negative quantity, and is the fall in demand price caused by the increase in the amount of villa accommodation offered by the builder. We have to make some study of the relative magnitudes of these two elements, P by the change in beta and beta by the change in P. If the builder monopolized the supply of villas, beta would represent the total supply of them, and if it happened that the elasticity of the demand for them was less than unity, when the amount beta was offered, then by increasing his supply he would diminish his total receipts, and P by the change in beta plus beta by the change in P would be a negative quantity. But of course he would not have allowed the production to go just up to an amount at which the demand would be thus inelastic. The margin which he chose for his production would certainly be one for which the negative quantity beta by the change in P is less than P by the change in beta, but not necessarily so much less that it may be neglected in comparison. This is a dominant fact in the theory of monopolies discussed in Book 5, Chapter 14. It is dominant also in the case of any producer who has a limited trade connection which he cannot quickly enlarge. If his customers have already as much of his wares as they care for, so that the elasticity of their demand is temporarily less than unity, he might lose by putting on an additional man to work for him, even though that man would work for nothing. This fear of temporarily spoiling a man's special market is a leading influence in many problems of value relating to short periods, and especially in those periods of commercial depression, and in those regulations of trade associations, formal and informal, which we shall have to study in the second volume. There is an allied difficulty in the case of commodities, of which the expense of production diminish rapidly with every increase in the amount produced. But here the causes that govern the limits of production are so complex that it seems hardly worth while to attempt to translate them into mathematical language. When, however, we are studying the action of an individual undertaker, with a view of illustrating the normal action of the causes which govern the general demand for the several agents of production, it seems clear that we should avoid cases of this kind. We should leave their particular features to be analysed separately in special discussions, and take our normal illustration from a case in which the individual is only one of many who have efficient if indirect access to the market. If beta by the change in P be numerically equal to P by the change in beta, where beta is the whole production in a large market, and an individual undertaker produced beta dash, 1,000th part of beta, then the increased receipt from putting on an additional man is P by the change in beta dash, which is the same as P by the change in beta, and the deduction to be made from it is only beta dash by the change in P, which is 1,000th part of beta by the change in P, and may be neglected. For the purpose, therefore, of illustrating a part of the general action of the laws of distribution, we are justified in speaking of the value of the net product of the marginal work of any agent of production as the amount of that net product taken at the normal selling value of the product, that is, as P by the change in beta. It may be noticed that none of these difficulties are dependent upon the system of division of labour and work for payment, though they are brought into prominence by the habit of measuring efforts and satisfactions by price, which is associated with it. Robinson Crusoe, erecting a building for himself, would not find that an addition of 1,000th part to his previous accommodation increased his comfort by 1,000th part. What he added might be of the same character with the rest, but if one counted it in at the same rate of real value to him, one would have to reckon for the fact that the new part made of the old somewhat less urgent need, of somewhat lower real value to him. On the other hand, the law of increasing return might render it very difficult for him to assign its true net product to a given half-hour's work. For instance, suppose that some small herbs, grateful as condiment and easily portable, grow in a part of his island, which it takes half a day to visit, and he has gone there to get small batches at a time. Afterwards he gives a whole day, having no important use, to which he can put less than half a day, and comes back with 10 times as great a load as before. We cannot then separate the return of the last half hour from the rest. Our only plan is to take the whole day as a unit, and compare its return of satisfaction with those of days spent in other ways, and in the modern system of industry we have the similar but more difficult task of taking for some purposes the whole of a process of production as a single unit. It would be possible to extend the scope of such systems of equations as we have been considering, and to increase their detail, until they embraced, within themselves, the whole of the demand side of the problem of distribution. But while a mathematical illustration of the mode of action of a definite set of causes may be complete in itself, and strictly accurate within its clearly defined limits, it is otherwise with any attempt to grasp the whole of a complex problem of real life, or even any considerable part of it, in a series of equations. For many important considerations, especially those connected with the manifold influences of the element of time, do not lend themselves easily to mathematical expression. They must either be omitted altogether, or clipped and pruned till they resemble the conventional birds and animals of decorative art. And hence arises a tendency towards assigning wrong proportions to economic forces, those elements being most emphasized, which lend themselves most easily to analytical methods. No doubt this danger is inherent in every application not only of mathematical analysis, but of analysis of any kind, to the problems of real life. It is a danger which more than any other the economist must have in mind at every turn, but to avoid it altogether would be to abandon the chief means of scientific progress, and in discussions written specially for mathematical readers it is no doubt right to be very bold in the search for wide generalizations. In such discussions it might be right, for instance, to regard H as the sum of total satisfactions, and V as the sum total of dissatisfactions, efforts, sacrifices, etc., which accrue to a community from economic causes. To simplify the notion of the action of these causes by assumptions similar to those which are involved, more or less consciously, in the various forms of the doctrine that the constant drift of these causes is towards the attainment of the maximum satisfaction in the net aggregate for the community, or, in other words, that there is a constant tendency to make H minus V a maximum for society as a whole. On this plan, the resulting differential equations, of the same class as those which we have been discussing, will be interpreted to represent value as governed in every field of economics by the balancing of groups of utilities against groups of disutilities, of groups of satisfactions against groups of real costs. Such discussions have their place, but it is not in a treatise such as the present, in which mathematics are used only to express in terse and more precise language those methods of analysis and reasoning which ordinary people adopt, more or less consciously, in the affairs of everyday life. It may indeed be admitted that such discussions have some points of resemblance to the method of analysis applied in Book 3 to the total utility of particular commodities. The difference between the two cases is mainly one of degree, but it is of a degree so great as practically to amount to a difference of kind. For in the former case we take each commodity by itself and with reference to a particular market, and we take careful account of the circumstances of the consumers at the time and place under consideration. Thus we follow, though perhaps with more careful precautions, the practice of ministers of finance and of the common man when discussing financial policy. We note that a few commodities are consumed mainly by the rich, and that in consequence their real total utilities are less than is suggested by the money measures of those utilities. But we assume with the rest of the world that as a rule, and in the absence of special causes to the contrary, the real total utilities of two commodities that are mainly consumed by the rich stand to one another in about the same relation as their money measures do, and that the same is true of commodities the consumption of which is divided out among rich and middle class and poor in similar proportions. Such estimates are but rough approximations, but each particular difficulty, each source of possible error, is pushed into prominence by the definiteness of our phrases. We introduce no assumptions that are not latent in the practice of ordinary life, while we attempt no task that is not grappled with in a rougher fashion, but yet to good purpose, in the practice of ordinary life. We introduce no new assumptions, and we bring into clear light those which cannot be avoided. But though this is possible when dealing with particular commodities with reference to particular markets, it does not seem possible with regard to the innumerable economic elements that come within the all-embracing net of the doctrine of maximum satisfaction. The forces of supply are especially heterogeneous and complex. They include an infinite variety of efforts and sacrifices, direct and indirect, on the part of people in all varieties of industrial grades. And if there were no other hindrance to giving a concrete interpretation to the doctrine, a fatal obstacle would be found in its latent assumption that the cost of rearing children and preparing them for their work can be measured in the same way as the cost of erecting a machine. For reasons similar to those given in this typical case, our mathematical notes will cover less and less ground as the complexity of the subjects discussed in the text increases. A few of those that follow relate to monopolies, which present some sides singularly open to direct analytical treatment, but the majority of the remainder will be occupied with illustrations of joint and composite demand and supply, which have much in common with the substance of this note, while the last of that series, Note 21, goes a little way towards a general survey of the problem of distribution and exchange, without reference to the element of time, but only so far as to make sure that the mathematical illustrations used point towards a system of equations which are neither more nor less in number than the unknowns introduced into them. Note 14 bis. In the diagrams of Chapter 6 of Book 5, the supply curves are all inclined positively, and in our mathematical versions of them we shall suppose the marginal expenses of production to be determined with a definiteness that does not exist in real life. We shall take no account of the time required for developing a representative business with the internal and external economies of production on a large scale, and we shall ignore all those difficulties connected with the law of increasing return which are discussed in Book 5, Chapter 12. To adopt any other course would lead us to mathematical complexities which, though perhaps not without their use, would be unsuitable for a treatise of this kind. The discussions, therefore, in this and the following notes must be regarded as sketches rather than complete studies. Let the factors of production of a commodity A be A1, A2, etc., and let their supply equations be y equals phi1 of x, y equals phi2 of x, etc. Let the number of units of them required for the production of x units of A be m1x, m2x, respectively, where m1, m2 are generally not constants but functions of x. Then the supply equation of A is y equals phi of x equals m1 phi1 of m1x plus m2 phi2 of m2x, and so on, which is equivalent to the sum of m phi of mx. Let y equals function of x be the demand equation for the finished commodity. Then the derived demand equation for AR, the rth factor, is y equals function of x minus phi of x minus mr phi r of mrx. But in this equation y is the price not of one unit of the factor but of m units, and to get an equation expressed in terms of fixed units, let eta be the price of one unit, and let xi equal mrx. Then n equals 1 over mr multiplied by y, and the equation becomes eta equals function r of xi equals 1 over mr by function of 1 over mr xi minus phi of 1 over mr xi minus mr theta r of xi. If mr is a function of x, say, equals psi r of x, then x must be determined in terms of xi by the equation xi equals x psi r of x, so that mr can be written chi r of xi. Substituting this, we have eta expressed as a function of xi. The supply equation for AR is simply eta equals phi r of xi. Note 15. Let the demand equation for knives be y equals f of x, 1. Let the supply equation for knives be y equals phi of x, 2. And let that for handles be y equals phi 1 of x, 3. And that for blades be y equals phi 2 of x, 4. Then the demand equation for handles is y equals function 1 of x equals function of x minus phi 2 of x, 5. The measure of elasticity for 5 is minus x f-1 of x over f1 of x to the power minus 1. That is minus x f dash of x minus x phi dash 2 of x over f1 of x to the power minus 1. That is minus x f dash of x over f of x multiplied by f of x over f1 of x plus x phi dash 2 of x over f1 of x to the power minus 1. This will be the smaller the more fully the following conditions are satisfied. 1. That minus x f dash of x over f of x, which is necessarily positive, be large, i.e. that the elasticity of the demand for knives be small. 2. That phi dash 2 of x be positive and large, i.e. that the supply price for blades should increase rapidly with an increase and diminish rapidly with a diminution of the amount supplied. And 3. That f of x over f1 of x should be large, that is, that the price of handles should be but a small part of the price of knives. A similar but more complex inquiry leads to substantially the same results when the units of the factors of production are not fixed but vary, as in the preceding note. Note 16. Suppose that m bushels of hops are used in making a gallon of ale of a certain kind, of which in equilibrium x dash gallons are sold at a price y dash equals function of x dash. Let m be changed into m plus the change in m, and as a result, when x dash gallons are still offered for sale, let them find purchasers at a price y dash plus the change in y dash. Then the change in y dash over the change in m represents the marginal demand price for hops. If it is greater than their supply price, it will be to the interest of the brewers to put more hops into the ale. Or, to put the case more generally, let y equal function of x and m, y equal phi of x and m, be the demand and supply equations for beer, x being the number of gallons and m the number of bushels of hops in each gallon. Then function of x and m minus phi of x and m equals the excessive demand over supply price. In equilibrium, this is of course 0, but if it were possible to make it a positive sum by varying m, the change would be affected. Therefore, assuming that there is no perceptible change in the expense of making the beer other than what results from the increased amount of hops, the differential of f over the differential of m equals the differential of phi over the differential of m. The first represents the marginal demand price, and the second the marginal supply price of hops, and these two are therefore equal. This method is of course capable of being extended to cases in which there are concurrent variations in two or more factors of production. Note 17. Suppose that a thing, whether a finished commodity or a factor of production, is distributed between two uses, so that the total amount x of the part devoted to the first use is x1, and that devoted to the second use is x2. Let y equal phi of x be the total supply equation, y equals f1 of x1 and y equals f2 of x2 be the demand equations for its first and second uses. Then in equilibrium the three unknowns x, x1 and x2 are determined by the three equations f1 of x1 equals f2 of x2 equals phi of x, x1 plus x2 equals x. Next, suppose that it is desired to obtain separately the relations of demand and supply of the thing in its first use on the supposition that, whatever perturbations there may be in its first use, its demand and supply for the second use remains in equilibrium, i.e. that its demand price for the second use is equal to its supply price for the total amount that is actually produced, i.e. f2 of x2 equals phi of x1 plus x2, always. From this equation we can determine x2 in terms of x1 and therefore x in terms of x1, and therefore we can write phi of x equals psi of x1. Thus the supply equation for the thing in its first use becomes y equals psi of x1, and this, with the already known equation y equals f1 of x1, gives the relations required. Note 18. Let A1, A2, etc. be joint products M1x, M2x, of them severally being produced as the result of x units of their joint process of production, for which the supply equation is y equals phi of x. Let y equals f1 of x, y equals f2 of x, etc. be their respective demand equations. Then in equilibrium, m1 f1 of m1x plus m2 f2 of m2x, etc. equals phi of x. Let x dash be the value of x determined from this equation. Then f1 of m1x dash, f2 of m2x dash, etc. are the equilibrium prices of the several joint products. Of course, m1, m2 are expressed, if necessary, in terms of x dash. Note 19. This case corresponds, mutatis mutandis, to that discussed in Note 16. If, in equilibrium, x oxen annually are supplied and sold at a price y equals phi of x, and each ox yields m units of beef, and if breeders find that by modifying the breeding and feeding of oxen they can increase their meat yielding properties to the extent of the change in m units of beef, the hides and other joint products being on the balance unaltered, and that the extra expense of doing this is the change in y then the change in y over the change in m represents the marginal supply price of beef. If this price were less than the selling price, it would be to the interest of breeders to make the change. Note 20. Let A1, A2, etc. be things which are fitted to subserve exactly the same function. Let their units be so chosen that a unit of any one of them is equivalent to a unit of any others. Let their several supply equations be y1 equals phi 1 of x1, y2 equals phi 2 of x2, and so on. In these equations let the variable be changed, and let them be written x1 equals psi 1 of y1, x2 equals psi 2 of y2, and so on. Let y equals f of x be the demand equation for the service for which all of them are fitted. Then in equilibrium x and y are determined by the equations y equals f of x equals x1 plus x2, and so on, y equals y2, and so on to y. The equations must be such that none of the quantities x1, x2, etc. can have a negative value. When y1 has fallen to a certain level, x1 becomes 0, and for lower values x1 remains 0, it does not become negative. As was observed in the text, it must be assumed that the supply equations all conform to the law of diminishing return, i.e. that phi 1 of x, phi 2 of x, etc. are always positive. Note 21. We may now take a bird's eye view of the problems of joint demand, joint supply, and composite supply, when they all arise together, with the object of making sure that our abstract theory has just as many equations as it has unknowns, neither more nor less. In a problem of joint demand, we may suppose that there are n commodities A1, A2, etc. to An. Let A1 have lowercase a1 factors of production, let A2 have lowercase a2 factors, and so on, so that the total number of factors of production is lowercase a1 plus lowercase a2 plus lowercase a3, and so on to lowercase an. Let this equal m. First, suppose that all the factors are different, so that there is no composite demand, that each factor has a separate process of production, so that there are no joint products, and lastly that no two factors subserve to the same use, so that there is no composite supply. Then we have 2n plus 2m unknowns, viz. the amounts and prices of n commodities and of m factors, and to determine them we have 2m plus 2n equations, viz. 1. n demand equations, each of which connects the price and the amount of a commodity, and 2. n equations, each of which equates the supply price for any amount of a commodity to the sum of the prices of corresponding amounts of its factors. 3. m supply equations, each of which connects the price of a factor with its amount, and lastly 4. m equations, each of which states the amount of a factor which is used in the production of a given amount of the commodity. Next, let us take account not only of joint demands but also of composite demand. Let beta 1 of the factors of production consist of the same thing, say carpenter's work of a certain efficiency. In other words, let carpenter's work be one of the factors of production of beta 1 of the n commodities A1, A2 and so on. Then, since the carpenter's work is taken to have the same price in whatever production it is used, there is only one price for each of these factors of production, and the number of unknowns is diminished by beta 1 minus 1. Also, the number of supply equations is diminished by beta 1 minus 1, and so on for other cases. Next, let us in addition take account of joint supply. Let gamma 1 of the things used in producing the commodities be joint products of one and the same process. Then the number of unknowns is not altered, but the number of supply equations is reduced by gamma 1 minus 1. This deficiency is however made up by a new set of gamma 1 minus 1 equations connecting the amounts of these joint products, and so on. Lastly, let one of the things used to have a composite supply made up from delta 1 rival sources. Then, reserving the old supply equations for the first of these rivals, we have 2 by delta 1 minus 1 additional unknowns consisting of the prices and amounts of the remaining delta 1 minus 1 rivals. These are covered by delta 1 minus 1 supply equations for the rivals and delta 1 minus 1 equations between the prices of the delta 1 rivals. Thus, however complex the problem may become, we can see that it is theoretically determinate, because the number of unknowns is always exactly equal to the number of the equations which we obtain. Note 22. If y equals f1 of x, y2 equals f2 of x be the equations to the demand and supply curves respectively, the amount of production which affords the maximum monopoly revenue is found by making xf1 of x minus xf2 of x a maximum, that is, it is the root or one of the roots of the equation. d over d of x by xf1 of x minus xf2 of x equals 0. The supply function is represented here by f2 of x, instead of as before by phi of x, partly to emphasize the fact that supply price does not mean exactly the same thing here as it did in the previous notes, partly to fall in with that system of numbering the curves which is wanted to prevent confusion now that their number is being increased. Note 23. If a tax be imposed of which the aggregate amount is f of x, then in order to find the value of x which makes the monopoly revenue a maximum, we have d over d of x by xf1 of x minus xf2 of x minus f of x equals 0. And it is clear that f of x is either constant, as in the case of a license duty, or varies as xf1 of x minus xf2 of x, as in the case of an income tax. This equation has the same roots as it would have if f of x were 0. Treating the problems geometrically, we notice that if a fixed burden be imposed on a monopoly sufficiently to make the monopoly revenue curve fall altogether below 0x, and q' be the point on the new curve vertically below L, then the new curve at q' will touch one of a series of rectangular hyperbolas drawn with YO produced downwards for one asymptote and OX for the other. These curves may be called constant loss curves. Again, a tax proportionate to the monopoly revenue, and say m times that revenue, m being less than 1, will substitute for q', a curve each ordinate of which is 1 minus m by chi, the ordinate of the corresponding point on QQ', i.e. the point which has the same abscissa. The tangents in corresponding points on the old and new positions of QQ' will cut 0x in the same point, as is obvious by the method of projections. But it is a law of rectangular hyperbolas which have the same asymptotes that if a line be drawn parallel to one asymptote to cut the hyperbolas, and tangents be drawn to them at its points of intersection, they will all cut the other asymptote in the same point. Therefore, if Q'3 be the point on the new position of QQ' corresponding to Q3, and if we call G the point in which the common tangent to the hyperbola and QQ' cuts 0x, GQ'3 will be a tangent to the hyperbola which passes through Q'3, that is, Q'3 is a point of maximum revenue on the new curve. The geometrical and analytical methods of this note can be applied to cases such as are discussed in the latter part of section 4 in the text, in which the tax is levied on the produce of the monopoly. Note 23 bis. These results have easy geometrical proofs by Newton's method and by the use of well-known properties of the rectangular hyperbola. They may also be proved analytically. As before, let y equal f1 of x be the equation to the demand curve, y equals f2 of x, that to the supply curve, and that to the monopoly revenue curve is y equals f3 of x, where f3 of x equals f1 of x minus f2 of x. The equation to the consumer's surplus curve, y equals f4 of x, where f4 of x equals 1 over x for values between 0 and x, of f1 of a by the differential of a minus f1 of x. That to the total benefit curve is y equals f5 of x, where f5 of x equals f3 of x plus f4 of x equals 1 over x for values between 0 of x, of f1 of a by the differential of a minus f2 of x. A result which may of course be obtained directly, that to the compromise benefit curve is y equals f6 of x, where f6 of x equals f3 of x plus nf4 of x, consumer's surplus being reckoned in by the monopolist at n times its actual value. To find OL, that is, the amount of the sale of which will afford the maximum monopoly revenue, we have the equation d over d of x by xf3 of x equals 0, i.e. f1 of x minus f2 of x equals x by f-2 of x minus f-1 of x. The left-hand side of this equation is necessarily positive, and therefore so is the right-hand side, which shows, what is otherwise obvious, that if LQ3 be produced to cut the supply and the demand curves in Q and Q1 respectively, the supply curve at Q2, if included negatively, must make a greater angle with the vertical than is made by the demand curve at Q1. To find OW, that is the amount of the sale of which will afford the maximum total benefit, we have d over d of x of xf5 of x equals 0, i.e. f1 of x minus f2 of x minus xf-2 of x equals 0. To find OY, that is the amount of the sale of which will afford the maximum compromise benefit, we have d over d of x of xfx of x equals 0, i.e. d over d of x by 1 minus n xf1 of x minus xf2 of x plus n for values between 0 and x of f1 of a by the differential of a equals 0, i.e. 1 minus n by xf1 of x plus f1 of x minus f2 of x minus xf-2 of x equals 0. If OL equals C, the condition that OY should be greater than ON is that d over d of x by xf6 of x be positive when C is written for x in it, i.e. since d over d of x by xf3 of x equals 0 when x equals C, that d over d of x by xf4 of x be positive when x equals c, i.e. that f-1 of c be negative. But this condition is satisfied whatever be the value of c. This proves the first of the two results given at the end of chapter 14 of book 5, and the proof of the second is similar. The working of these results and of their proofs tacitly assumes that there is only one point of maximum monopoly revenue. One more result may be added to those in the text. Let us write OH equals A. Then the condition that OY should be greater than OH is that d over d of x by n f6 of x be positive when A is written for x. That is, since f1 of A equals f2 of A, that 1 minus n by f-1 of A minus f-2 of A be positive. Now f-1 of A is always negative, and therefore the condition becomes that f-2 of x be negative, i.e. that the supply obey the law of increasing return, and that the tangent of phi be numerically greater than 1 minus n by the tangent of theta, where theta and phi are the angles which tangents at A to the demand and supply curves respectively make with OX. When n equals 1, the sole condition is that the tangent of phi be negative, that is, OW is greater than OH, provided the supply curve at A be inclined negatively. In other words, if the monopolist regards the interest of consumers as identical with his own, he will carry his production further than the point at which the supply price, in the special sense in which we are using the term, is equal to the demand price, provided the supply in the neighbourhood of that point obeys the law of increasing return. But he will carry it less far if the supply obeys the law of diminishing return. Note 24. Let the change in x be the probable amount of his production of wealth in time, the change in t, and the change in y the probable amount of his consumption. Then the discounted value of his future services is r to the power minus t by the differential of x over the differential of t minus the differential of y over the differential of t for values between 0 and t, by dt for values between 0 and t, where t is the maximum possible duration of his life. On the like plan, the past cost of his rearing and training is r to the power minus t by the differential of y over the differential of t minus the differential of x over the differential of t by the differential of t for values between minus t dash and 0, where t dash is the date of his birth. And if we were to assume that he would neither add nor take from the material well-being of a country in which he stayed all his life, we should have r to the power minus t by the differential of x over the differential of t minus the differential of y over the differential of t by the differential of t for values between minus t and t equals 0. Or taking the starting point of time at his birth, and L equals t dash plus t equals the maximum possible length of his life, this assumes the simpler form r to the power minus t by the differential of x over the differential of t minus the differential of y over the differential of t by the differential of t for values between 0 and L equals 0. That is to say that the change in x is the probable amount of his production in time, the change in t. Is to put shortly what we may have more accurately expressed thus: let P1, P2, etc. be the chances that in time, the change in t, he will produce elements of wealth, the first change in x, the second change in x, etc., where P1 plus P2 and so on equals 1, and one or more of the series, the first change in x, the change in x, may be 0, then the change in x equals P1, first change in x, plus P2, second change in x, and so on. End of Mathematical Appendix. End of Principles of Economics.